Good evening and welcome to the St. Louis Zoo for the fifth program in our science seminar series co-sponsored by the Academy of Science. My name is Jim Jordan and I'm glad that I'm involved with this series that kind of keeps me up to date on current events in science, and we've had a great season so far, and tonight, even though we don't have quite the number of high school students, I've noticed a number of new faces coming in. We have one more program on March 25th, the Energy Environment Nexus, and it explores clean energy through new technologies, and we hope you come back for that. There's the opportunity to sign up to receive e-blasts of all kinds of free adult programs focusing on science. There'll be clipboards coming around. If you've already filled one out in a previous time, you don't need to repeat it, but there's many different venues now that you can take advantage, and I think St. Louis is becoming one of the leaders as far as public education on science. I'm going to turn it over to Rose Jansen from the Academy of Science, who will introduce our speaker, John Rigden.
Well, good evening. This is a science seminar series that's a partnership series of the Academy of Science St. Louis and the St. Louis Zoo. And for those of you who are not familiar with us, I know many of you are, I'm going to take just a moment to tell you a little bit about who we are. We are a local nonprofit that's been serving the St. Louis community and surrounding counties since 1856. We have a long-standing mission to advance the public understanding of science and inspire the next generation of scientists and science advocates. And we do that through a number of broad range and free, low-cost or low-cost public science programming, collaborative seminar series, and trips and tours that highlight science at venues throughout the region. And you can find more information on the Academy and our community-wide events and programs by visiting our website at academyofsciencestl.org or by picking up some of our literature just outside the auditorium on your way out this evening. If you'd like to receive e-notification of upcoming Academy and St. Louis Zoo public lectures and events, there are e-news sign-up sheets that will make their way around the audience tonight, and there's one outside the auditorium as well. There are brochures available to take with you on your way out this evening, and with that, and then I'd also like to mention Friday, if you have an interest, we have another public seminar at Clayton on the Park on advising the U.S. President. Who advises the U.S. President on science and scientific matters with Michael Friedlander from Washington University. So there's information on that as well outside the auditorium and on our website. And with that said, I'd like to introduce tonight's speaker, Dr. John Rigden. Dr. Rigden's scholarly work is in the areas of molecular physics and the history of science. He is an honorary professor of physics at Washington University in St. Louis, a fellow of the American Association for the Advancement of Science and the American Physical Society, and a 2008 recipient of the Academy of Science St. Louis's Outstanding St. Louis Scientist Educators Award. He received his B.S. from Eastern Nazarene College and his Ph.D. from Johns Hopkins University and was a postdoc fellow at Harvard University. Dr. Rigden has served on the faculties of Eastern Nazarene College, Middlebury College, and the University of Missouri St. Louis. In 1987, he joined the American Institute of Physics, where he served as Director of Physics Programs. For 10 years, he was editor of the American Journal of Physics, and in 1992, he was the Director of Development of the National Science Standards Project at the National Academy of Sciences. He served as an NSF consultant to India in 1968 and 69, was the United States representative to the International Science Exhibition in Rangoon, Burma in 1970, a Fulbright Fellow to Burma in 1971 and to Uruguay in 1975. He is the author of Physics and the Sound of Music, Ravi Scientist and Citizen, and Hydrogen, the Essential Element, which will be available for purchase and signing by the author tonight, just down here in front of the stage. And we're very pleased to have Dr. Rigden here with us tonight to talk about how the simplest atom offers evidence for the Big Bang. So on behalf of the Academy of Science and the St. Louis Zoo, won't you please welcome Dr. John Rigden.
No problem.
Well, thank you very much. It's nice to see a group of people here to learn, I hope, a little something and be entertained maybe a little bit. In any event, I'm glad to be here. Some of the things that Rose mentioned, golly, almost forgot some of those. But there were a lot of good things in there. I mean, good from the point of view of experience and helping serve the interests of science. I want to deconstruct that title just a bit. Hydrogen, the atom of the universe. Start there. Why? Why is it the atom of the universe? Well, to begin, 90% of all atoms in the universe are hydrogen. Did you know that? How many knew that? 90%. The other 10% are helium. And that leaves a few grains of salt and pepper for all the other elements. Just a sprinkling, all right? So hydrogen is 90% of all the atoms in the universe. Our sun, as well as all other stars, are essentially all hydrogen. Our sun burns 600 million tons of hydrogen every second. Did you get that? 600 million tons per second. It's going to live for 5 billion years yet. Sun's a big thing. A lot of hydrogen. And that burning of hydrogen produces a temperature in the core of the sun of 27 million degrees Fahrenheit. With numbers like that, it doesn't matter whether it's Celsius or Fahrenheit. And the heat from this 27 million degree core slowly makes its way through 432,000 miles of surrounding sun. Now, these are not big numbers. From the core, 27 million degrees, that heat slowly makes its way. In fact, slowly. It takes about 10 million years, that heat, to get from the core out to the surface of the sun. And once it's out to the surface, it maintains a surface temperature for the sun of about 10,000 degrees. And that 10,000 degree body radiates warmth and heat in all directions. And in one of those directions, about 92 million miles away, there's a little blue planet. And the warmth from this sun maintains an average temperature on this little blue planet of 57 degrees Fahrenheit, which makes possible things like mosquitoes, armadillos, horses, and George W. Bush. So we have a lot to be thankful for. Well, indeed, hydrogen is the atom of the universe. Now, and hydrogen provides a check on Big Bang cosmology. What does that mean? Well, that's a question that'll take a few sentences to answer. There are other subjects that cannot be, or questions that cannot be answered simply in a sentence. For example, how should we solve the economic problem of the United States? If you ask 6 economists that question, you're going to get 4.5 different answers. You know that. Now, if you ask 6 physicists, how is it that hydrogen provides a check on Big Bang cosmology, you'll probably get 6 answers all the same. Because this is something we know pretty well. So we can answer that question, and that's a question that I want to try to answer this evening. So I made my case that hydrogen probably was the one word that God used to create the whole picture that we watch through our lives. Now, I suspect many of you are interested in antiques. I have an antique here that is not 100 years old. It's not 1,000 years old. It's not 1,000,000 years old. It's not 1,000,000,000 years old. It is 14.5 billion years old. Here it is. Now, I don't know if you can see this. If you can't see this, you can see this. The only difference between these two is that I know something about this. I know how much is in there. It's water. And water is made up of 2 hydrogen atoms and 1 oxygen atom, which is why we call it H2O. Now, the hydrogen atom is a very simple atom. 1 nucleus, spent in absolute isolation. It is surrounded by an electron, in orbit more or less, but really not in orbit. The electron surrounds, in a way, the nucleus. But it is so far away from the nucleus that the nucleus hardly knows it's there. Picture, for example, our sun and 1 planet, Pluto. Earth is much too close for the electron to be. Jupiter's too close. Neptune is too close. Actually, Pluto is too close. But it's the furthest one out there. So think of the sun and Pluto. And that's the hydrogen atom. All the empty space between the nucleus and the electron is like all the empty space between the sun and Pluto. Okay? Now, you may not know, but you probably do, many of you, that there's 2 forms of hydrogen that we're very much aware of because they're, in a way, around us. The 2 forms of hydrogen are ordinary hydrogen and heavy hydrogen. Heavy hydrogen has a more massive nucleus. In fact, the nucleus of heavy hydrogen is twice as massive as the nucleus of hydrogen. Otherwise, they're identical. The electron is way out there, just the same as with ordinary hydrogen. It acts just like the 2 of them act just the same chemically. But we have 2 types, ordinary and heavy. Now, in this vial are both ordinary and heavy hydrogen. In this water The heavy tastes great. Both kinds of hydrogen. For every 10,000 ordinary hydrogen atoms here, in this, and in this, there are 2 heavy hydrogen atoms. So it's a very small percentage of hydrogen is heavy hydrogen. Now, the thing about heavy hydrogen is that it's 14.5 billion years old. I hold in my hand stuff from the very beginning of time. 14.5 billion years old. Now, those are big numbers. We've talked some big numbers, but I trust that you are now accustomed to big numbers. You know, 14.5 billion is just 1/1000th of our national debt. We're used to big numbers like the national debt. We live with that, right? So when we say 14.5 billion, hey, that's nothing. Well, water, hydrogen, there are 20 billion heavy hydrogen atoms in this little bit of water. Now you can do the arithmetic. For every 10,000 ordinary hydrogen, there are just 2 heavy hydrogen. And yet, there are 20 billion heavy hydrogen atoms in this sample of, I'm sorry, did I say 20? I meant 20,000 billion. Okay, so here is hydrogen, which is very old. And the fact that the universe is also 14.5 billion years old, and this deuterium is 14.5 billion years old, tells you immediately that there's a connection. And it's that connection which provides a real check on Big Bang cosmology. Well, all right. That's a story, you know, if it's been around for 14.5 billion years, it has a story to tell. It's been through a lot. And I'm going to tell you the story of this little atom. And we're going to start the story in 1885. 19th century. And it begins in Basel, Switzerland. There was a mathematics teacher in an all-girls high school. His name was Johann Vollmer. And Vollmer, as a mathematician, became interested in 4 numbers. Let me tell you what the numbers were. The numbers were, well, 14.5 billion years ago, and here we are, okay? The 4 numbers were, and we're going to come back to these, the 4 numbers were 6562, 4861, 4340, 4101. They're not pretty numbers. In fact, they're sort of ugly numbers. But Vollmer was interested in those numbers. Now, the reason he was interested in them is because they were special. And those special numbers are going to come back to us this evening. They play a central role. He became absolutely caught up with trying to understand if there was a connection between them. Here's why. How many have seen a rainbow splashed across your dining room wall? How many have seen that? Or family room wall? You know what it is. It's the sunlight coming through a glass knick-knack on the windowsill, or the sunlight coming through a crystal hanging from a chandelier, and the light going through that crystal provides a rainbow. Red through blue, through violet. All the colors are there. The colors are continuous. The red merges seamlessly into the orange, and the orange seamlessly into the yellow, and so on, all the way through blue. This is the rainbow. Rainbows are beautiful. There are colors. Well, if you take a tube of hydrogen gas, like you take a tube, let's say, of neon, a fluorescent tube, put it in your light fixture, and an electric voltage of sorts will be across the ends of that, and something of a discharge will get set up, and that fluorescent tube will light. And many of you have fluorescent lights at home. You can do the same thing with hydrogen. You can set up a hydrogen tube, put a discharge across it, and what you get is not a continuous rainbow, but 4 distinct colors. Notice the light from the hydrogen discharge. That's a tube of hydrogen. And it emits light. And that light we have going through a slit so that the light is collimated through the crystal from your chandelier. And then out comes not this, not a continuous rainbow, but 4 distinct colors. This is something unique to hydrogen. Now, a Swedish physicist by the name of Anders Ångström measured the wavelengths of those 4 light rays, or whatever you want to call them. He measured their wavelengths. Well, here's what you would get if you put a piece of paper up there and let those 4 beams shine on the piece of paper. You'd see 4 lines. Each of those is an image of the slit. So here's the difference. Sunlight, all colors, many wavelengths. The hydrogen atom, select colors and select wavelengths. Now, here are the results of Ångström's measurements. Those are the numbers. Those are the very numbers that Vollmer was interested in. Now, Vollmer recognized that all of these numbers come out of the hydrogen atom somehow. They're connected to the hydrogen atom. It's not like a pound of meat at Deerberg's. There's a number. And the price of gas down on Manchester, there's another number. And the height of your uncle in Omaha, there's another number. But there's no connection between those numbers. There's obviously no connection between those numbers. But these numbers, which are the wavelengths of light given off by hydrogen, are seductive. And they were certainly seductive to the high school teacher in Basel, Switzerland, Mr. Vollmer. And Mr. Vollmer wanted to know if there was some way of connecting those numbers. So he started looking. I have no idea how long he looked. And I'm assuming that his approach was very much a trial and error approach. But he kept working, and what he ended up with and what he got was an equation. Now, I don't want you to even think about that equation. You don't need to know a thing about that equation, except there it is. And I just want to point out one thing. This is just a number. B is that. N is just a number, 2. But M can have the value 3. Stick 3 in there and solve it. 4, stick 4 in there and solve it. 5, and so forth. So here's an equation, a formula that Vollmer got to, which linked those 4 wavelengths of the hydrogen atom. Look at that. If that doesn't impress the dickens out of you, look at that. Here is Ångström's measured value. Here's Vollmer's calculated value. With that formula I just showed you, with m equals 3. With m equals 3, Vollmer calculated 6562. Ångström measured 6562. That's pretty damn good. With 4, you can't see that very well. With m equals 4, Ångström measured 4861. Vollmer calculated 4861. Looks good. Looks good. That is what you call good agreement between theory, a calculated value, and a measured value. Only it's not theory. Theory does much more than that. You see, this formula that allowed Vollmer to calculate these numbers, which agreed exactly with the measured numbers, that had to make him feel good. But these calculated numbers and this formula tells you absolutely nothing. That formula tells you nothing about how those lines are being generated. What's going on inside the hydrogen atom that enables those lines to come out with those wavelengths that this formula is able to reproduce. Well, everything changed. Everything changed when Vollmer did this. All of a sudden, people knew that the atom had some internal parts or some internal ways of generating these wavelengths. Something very specific. Vollmer himself knew. Vollmer says, it seems to me that hydrogen, more than any other substance, is destined to open new paths to the knowledge of the structure of matter and its properties. In this respect, the numerical relations among the wavelengths of the first 4 hydrogen spectral lines should attract our attention particularly. This in 1885. Vollmer knew he had done something, and everyone else did it too. Here's a comment from Ted Hench. He's in Munich. Historically, the simple and regular Vollmer spectrum has inspired path-breaking discoveries. Well, that's absolutely true. Okay, so here are now these 4 lines, and we're going to see them come back. at the beginning of creation. All right. Now, let me just give you an aside. Vollmer was a high school teacher. I know of one other high school teacher, Joseph Henry. Have you ever heard the name? The unit, the unit, let's say, of distance is a mile. You go so many miles. The unit of magnetic induction is the Henry. Joseph Henry was a high school teacher in Albany, New York, an all-girls school. Vollmer, an all-girls school. Henry, an all-girls school. You have to ask, what does being in an all-girls school do to these guys? I haven't seen many high school teachers coming up with fundamental new stuff that lives through the ages. I haven't seen very many. But Vollmer and Henry are two. Okay. Now, we're going to switch gears from these numbers and these wavelengths and the hydrogen atom right now. And we're going to go not from first to second, which is pretty trivial. We're going to go from angstroms, wavelengths, to light years. From atoms to galaxies. During the 20th century, we have discovered some fundamental things about our universe. Do you know, as recently as 80 years ago, we all thought, if you were sitting here 80 years ago, 1929, you would have thought, or you would be under the impression, that the Milky Way was the universe. That was the universe. We thought that was it. Now it's big. How big is the Milky Way? 20 miles? It's about 100,000 light years across. You know what that means? It means light traveling at 186,000 miles a second. Almost 200,000 miles a second. Takes 100,000 years to get across the Milky Way. You know, cosmic things, they're big scale stuff. Well, 100,000, where are we, by the way? Where are we in the Milky Way? We're about halfway out from the center. We're at about 30,000 light years from the center. Remember, 100,000 across, so 50,000 from center to one edge, roughly. Now, there's no edge, but, it peters out. The stars get less dense, and pretty soon, you're sort of out of the galaxy. We're about 30,000 light years from the center. And our sun is moving through the galaxy on a big orbit, about 30,000 light years in radius. It's moving through the galaxy at 600,000 miles per hour. You, right now, you're whipping along at 600,000 miles per hour and you don't even know it. The sun holds the earth to it. We're a captive of the sun. And the sun is moving along its orbit 600,000 miles an hour. I don't even feel a breeze in my face. But that's where we are. All right, now, in 1929, 80 years ago, Edwin Hubble was looking at nebula, clouds, smeary things that you can see if you look through a telescope and look up into the sky. You can see them. Oh, wait a minute. I don't know if you can see this. Hydrogen, the only reason Vollmer succeeded was that hydrogen is simple. One nucleus, one electron. It's simple. And here, notice, here's one of the lines. Here's another line. There's sort of, look, I don't know, and here's a, you can't see this as a dark, maybe you can, dark blue line there. The next element, helium. Already there's a line here, not one, not four, line here, line, a very faint line here, a bright line there, bright line here, faint line here, two lines here, one line here, a bit of a line here, a faint line here. Helium, that's number 2. If Vollmer had tried to do something with helium, he'd have failed. Helium's complicated. 3 particles, the nucleus and 2 electrons. Hydrogen is simple. Here's old oxygen. Here's old oxygen, that attacks iron and is the great oxidizer. But look how complicated that is. Look at all these lines. Vollmer would never have gotten to first base if he'd have screwed around with oxygen. He wouldn't have gotten anything. But hydrogen, with just its 4 lines, allowed Vollmer to succeed, and hydrogen became the trailblazer for all the other investigations into atomic structure and into the nature of matter. All right? Now, here is a nebula. This is in Orion. This is in the Milky Way. But here is a cloud of hydrogen. All right? That's what Hubble was looking at in 1929. Some of your parents were alive. Maybe some of you were alive. This one is inside the Milky Way. Now here's a large Magellanic Cloud. This is 160,000 light years away. This is outside of the Milky Way. But what Hubble was doing was looking at these nebula. And he looked at another nebula, this one. Now if you look at this on a clear night, you can see a little smudge in the sky. That's Andromeda, the great galaxy that's near Milky Way, 2 million light years from us. But it's a close one. This is a big galaxy. Well, with work from a couple others, Hubble was able to identify specific and isolate specific stars in this nebula, and he realized it was not a nebula. He realized it was another galaxy. Oh, they didn't even know the word galaxy then, but it became known as a galaxy, an island universe. This became known as Andromeda, a big galaxy, bigger than the Milky Way. And now, all of a sudden, the universe had gotten much bigger. No longer just the Milky Way. Now we had another galaxy, 2 million light years away. Okay? Hubble kept looking. Here is a little patch of sky. Any patch of sky you look at, you can see covered with galaxies. All of these are galaxies. Each of these galaxies contain millions and millions and some billions and billions of stars. All right? So the universe is filled with galaxies. All right. That's what Hubble did. And he saw familiar Vollmer lines coming from these things. Now, he kept working. And what he discovered more was that as he looked at these galaxies, anywhere he looked at the galaxies, They were moving away from us. And the universe was expanding. That was a big one. We live in an expanding universe. Now, it doesn't mean that we're at the center and everything's moving away from us, that we're, you know. What it means is that the universe is like a loaf of bread, and we are a raisin in the bread, and any raisin we live on, you look at all the other raisins, and all the other raisins are moving away from you. Absolute. Every raisin, no matter which one you're on, is moving away from you. No matter which galaxy you are on in this universe, all the others are moving away from you. So we live in a universe where the galaxies are moving away and the universe is expanding. Any cosmology is going to have to face up to the fact that the universe is expanding. That's a fact. Now, another fact was discovered, and that fact was that there is a radiation that is everywhere in the universe. It's called the cosmic microwave background radiation. Have you heard of that? You've heard of that. Well, Penzias and Wilson discovered that with this big device, this big horn. They worked at AT&T Bell Labs, and they were trying to find out if there was any interference that would hassle people on their long-distance calls. There's transatlantic telephone calls. AT&T was interested in telephones. And so here's a big horn, a big detector for big, long wavelength radio waves. And they discovered a background that they could not get rid of, a hiss, a static. They had static all the time. They couldn't get rid of it. They did everything they could think of. Pigeons love this thing. They got in there, and they pooped in there. And Penzias and Wilson thought that maybe the poop was radiating something. And so they cleaned out all the pigeon droppings. Didn't change a thing. And pretty soon they were forced to the conclusion that this hiss, this static, was something real. And it was coming from all directions. And that is called the microwave background radiation. Now, this background radiation and the expanding universe are seamlessly consistent with Big Bang cosmology. You start with a Big Bang, a lot of stuff goes out in all directions, you know, and that's the expanding universe. And we'll just in a moment I'll tell you where the background radiation comes from. But we have to go back to the beginning. We don't know anything before a tenth of a billionth of a second. We do, but not reliably. It's a commentary on physical theory, particularly Einstein's general relativity, that it can take us back to before a billionth of a second. We can't go back to zero of time. Because the universe, according to what we understand, had infinite density and infinite temperature. We can't do anything with infinities. The theories break down before we get to the zero of time. But to a billionth of a second after the Big Bang, we can go all the way back there with some reliability. Well, what was it like? In those very early fractions of a millisecond, everything consisted of particles, photons, electrons, protons, neutrons, neutrinos. They were going very rapidly, very fast, and crashing into each other. Nothing could form. As soon as a proton tried to grab hold of an electron, another particle would come and smash it apart. There was nothing that could stick together. It was a seething bunch of baloney stuff, you know, particles, just, all right. Now, from 1 second to 1,000 seconds, that part of the universe is when helium nuclei, a lot of helium nuclei, and all deuterium nuclei were formed. There is no mechanism in the universe to make deuterium today. All the deuterium in this glass of water, 2 deuterium for every 10,000 hydrogen. Every deuterium was made during the period from 1 second to 1,000 seconds. There's no other way it could have been made. Now, how do we know this? How do we know this? I'll tell you how we know it. A lot of work has gone on in high-energy physics laboratories, accelerators. Fermilab is not far from here. CERN over in Switzerland. We know very much about how particles like photons, electrons, protons, how they behave at very, very high energies. We know that. And we know that at 300,000 years, now we're jumping ahead, at 300,000 years, the temperature had gotten cool enough, about 3,000 degrees, that atoms could form. Protons could reach out and grab a positive proton and grab a negative electron, and an atom of hydrogen form. Atoms formed at about 3,000 years, 3,000 years, 300,000 years, at a temperature of 3,000 degrees. 300,000 years after the Big Bang. And when atoms formed, 90% were hydrogen and 10% were helium. Now, that's background. We know that the deuterium atoms that we have in our water today originate 14.5 billion years ago. Now, here's what. Here are 2 guys. One is David Schramm. He's on the left. And this one is Michael Turner. He's on the right. These 2 guys said, look, we know how much deuterium we have, what the abundance of deuterium is right now today. We can figure out from the data in our laboratory different mechanisms that could give rise to deuterium back in that early time, 1 second to 1,000 seconds. And so they started doing calculations. And they calculated what the abundance of deuterium had to be back right after the Big Bang. Okay? Now let me just pause here a minute. David Schramm, University of Chicago, they were colleagues. David Schramm drove a red Porsche. He piloted his own plane. He was a big guy. He wrestled with Chicago Bear linemen, the NFL guys. And David held his own against those NFL guys. He piloted his own plane, as I said. He was going to Santa Fe. Plane crashed into a wheat field in Colorado. And at age 51 or 2, David was dead. Stephen Hawking said, there's no guy like David Schramm. Michael Turner, I was with last Saturday. And I talked about what we're going to talk about right now. Michael Turner is the guy. When the New York Times or Time Magazine or the media have a question about some new thing, they'll get a quote from Michael Turner. They'll call Chicago, and they'll get Michael Turner on the line. What's this all about, Professor Turner? And Michael will tell them what it's about, and they'll get a quote, and you'll read it in the paper, or you'll read it in the magazine. They're both amazing guys. Now, what they did was they did calculations from data. What's amazing is that here you have the world of particles. the extreme smallness of our work, linking up to try to understand something about the beginning of the universe. The biggest thing we try to understand. So we go from the universe, big, down to the particles, small. But these two extremes have linked hands. And we're learning so much about the big cosmos from understanding the little particles that the big cosmos started out with. So, they did the calculation. Now remember, two deuterium atoms for every 10,000 hydrogen. And there's no place else. That's today. Deuterium does get destroyed in stars and so forth. It can get, so back there, it had to be a little higher. We would think it had to be higher. They calculated 3.5 deuterium atoms per 10,000 hydrogen. Today we observe 2 per 10,000. Now, here's a calculation. What are you going to do? You say, okay, there's a calculation. Ha ha ha. How are you going to check it? This is a calculation about how much what was the abundance of deuterium back 100 seconds after the Big Bang, 1,000 seconds after the Big Bang. Well, what they did was they started looking for an old hydrogen cloud. You saw those nebula? Those are mostly, almost all hydrogen clouds. And they looked for an old hydrogen cloud. Old meaning it's far away. Why is far away old? Because if we see a hydrogen cloud that's 10 billion light years away, we're seeing the light that comes to us from that hydrogen cloud. We see it as it was 10 billion years ago. When you look up at a sky, see a star, see Andromeda, you're seeing Andromeda, which is 2 million light years away. No, 2 million miles away. You're not seeing it the way it is right now. You're seeing it the way it was, a couple hours ago, or whatever it is. All right. So they looked for an old cloud. And they found a cloud that I have been told is 14 billion light years away. Now, I put a big question mark on that. I'm not sure that's correct. But it's a long ways away. And now they wanted to check and see what the abundance of deuterium was 14 billion years ago, right at the beginning. How are they going to do that? You know what they did? Luckily, there was a quasar behind the hydrogen cloud. There was a quasar. A quasar is a very bright object. There's not many of them. Well, there's a few tens of thousands. Very bright, far away. And there was a quasar behind it, and the light from that quasar was shining through the hydrogen cloud. What do we see? What did we see when we saw that light shining through the hydrogen cloud? Well, that light excited some hydrogen atoms, and those hydrogen atoms gave off those famous 4 lines. But not only the 4 lines, it also gave off a little lower frequency, very faint. This is exaggerated. I had to draw it so you could see it. But here's the line that we looked at before. That's regular hydrogen. A little lower wavelength, smaller wavelength, is deuterium. So they saw, coming through this cloud, the light from that quasar, they saw spectral lines not only of hydrogen, but of deuterium. And from the intensities of those spectral lines, they were able to measure the abundance of deuterium as 1.9 to 2.5 deuterium per 10,000 hydrogen atoms. That's amazing, I mean, here was Schramm's and Turner's prediction, 3.5 deuterium per 10,000 hydrogen. Back 14 billion years ago. That's their prediction. They measure from this old 10, 12 billion year old cloud, which contains hydrogen and deuterium, and we're seeing it as it was 10, 12 billion years ago, soon after the Big Bang. And way back there, they measure that cloud had 1.9 to 2. This is the range, the range of error, allowing for errors. But when I asked Turner, I saw him last Saturday, I told you. I said, are these results still robust? He said, they're robust. You can believe in them. He said, I'm sorry, this should be getting a lot more attention. This is one of the most rigid checks on the Big Bang. This abundance of deuterium. Michael said, it should be a lot better known. And I said, Michael, I'm going to be talking to some people in St. Louis on Wednesday. I'm going to talk about your work. And he smiled. And he said, that's good. So, one of the most stringent, tight checks on the Big Bang comes from the abundance of deuterium. Today, 2 atoms for every 10,000. Back probably earlier, it was more like 3 or 3.5 or maybe 4, something like that. So, after the Big Bang, if Schramm's calculations and Schramm and Turner are correct, we had 3.5 for every 10,000. Today we have 1.5 or 2 for every 10,000. So they're pretty close. So Big Bang cosmology is supported absolutely by 3 major things. The expanding universe, the microwave background radiation, and I never did tell you where that came from. I'll tell you maybe later. And deuterium. So, I do believe that probably God did create the world with the Word. And probably the Word was hydrogen. So, it's a great element. It has been a trailblazer. So many things that we know today have come through hydrogen. That's it. Thank you very much. Now, if you have questions, I would be happy to struggle with them. Do you have any questions? Yes?
What's the background noise?
The background noise is this. Before 300,000 years, all particles were singular particles, positive protons, negative electrons, and photons, and neutrinos, and neutrons. These particles were too energetic to come together to form atoms. But by the time the temperature got down to 3,000 degrees, at about 300,000 years after the Big Bang, electrons and protons could come together and form atoms. And when you had an atom, you no longer had a charged particle. They were now electrically neutral. While they were charged, like take electrons, light interacts so strongly with those electrons that the light would go a milli-inch. It would hit an electron and then move away and hit another electron. Move away, hit another electron. It couldn't get away. It couldn't move. There were so many electrons, particles, charges around. Light was trapped in this plasma. It's like, the universe was opaque. It's like the wall of your family room. That's opaque. Sun doesn't get through the wall. Sun gets through your window. That's transparent. As soon as atoms were formed and these charges no longer existed, light was suddenly freed. And it started out winging its way through the universe. And today we see that light as the microwave background radiation. Only the wavelength, as the universe has expanded, the wavelength of that light is expanded, and it's now in the microwave domain. So the cosmic microwave background radiation was started, in a sense, as soon, and they call it decoupling of light from matter. Light was hooked to matter as long as the matter was all charge. But as soon as electrons and protons came together to form atoms, the light was freed, and the universe became transparent. And that light we still see in the form of the microwave radiation. That's where it comes from. It absolutely, it's like hand in glove. Any cosmology in 2400 will have to deal with expansion, cosmic microwave background radiation, deuterium. Now, by that time, they may have some more pieces of hardcore evidence. But for right now, those are three things any cosmology has to talk about and answer. Big Bang does that. Yes? Is what? Is it at the speed of light? Oh, no. Well, the galaxy's speed, they could not. No, they could not exceed the speed of light. But strange things can happen, which is a whole other story, and that would be another good topic. At some point, there is going to be parts of the universe which will be inaccessible to us because of relativistic considerations. Yes. At the early stage, I'm not going to say for sure.
I thought they were saying it did because space itself is expanding.
Are you talking about inflation? Are you talking about inflation? There was a period long before a billionth of a second, long before that, when the universe went through a very short period of rapid acceleration. It's called inflation. And this inflation is necessary in order to explain the distribution of galaxies. When you look at the universe, galaxies are, I showed you that one picture, full of galaxies. Any little postage stamp size of the sky you look at, it's full of galaxies. Why is matter distributed rather uniformly? Matter meaning galaxies. Why aren't they clumped up? What makes them distributed so nice? It's inflation that answers that problem, that question. And whether what's happened at that point, I'm not positive. Yes.
I'm not really sure how to answer the question. I think the answer is better than the question. What is the property of deuterium that prevents it from being created, say, like a supernova with other elements?
Well, okay. All right. The first thing you have to, helium nucleus is a very stable nucleus. In fact, uranium, for example, when uranium decays, it's a radioactive element, make bombs out of it, has a half-life of, oh God, I forget, something like a billion years or something. When it decays, it spits out an alpha particle, which is a helium nucleus. A very stable little collection of 2 protons and 2 neutrons. The deuterium is a very fragile nucleus. It will rupture at the slightest tick-a-two, you know. You hit it with a little finger, you know, and it's fragile. So it cannot exist in stars. The environment of stars is too energetic, too hot, too so forth, and deuterium atoms don't exist there. Now, when hydrogen collapses, a cloud of hydrogen collapses, like in that Orion Nebula that you saw, that's an incubator for new stars. New stars are being born in that. That's a big cloud of hydrogen. And that's got clumps, and clumps condense into big stars. And when they start, the deuterium is there, of course. There's a certain abundance of deuterium in it, but that deuterium gets destroyed. Okay? And there's no process to make it. The reason it stopped being made at around 1,000 seconds is that the density of matter got spread out enough that the probability of a neutron and a proton coming together to form the nucleus of deuterium was essentially zero. So, anyways. Yes, sir.
Does anybody know what caused the Big Bang in the first place?
No. You know, that's a wonderful question. I mean, it's a question that there are certain questions science can't answer. You know, why did it happen in the first place? I don't know. Nobody knows. Science can't answer that question. There's a lot of mysterious things if you stop thinking about it. You know, time and space. Basic physics is involved with a very few basic concepts. You know, there's only about 8 or 9 of them. We can explain the universe. We can explain the Earth. We can explain the solar system. We can explain a lot with very few things. They're powerful ideas. And when you get back to the Big Bang, things get very interesting. But there's so many things. I mean, there's so many things that come out of it. You know, for years, there was an alternate cosmology called the steady state. Remember that? The steady state had to make one hypothesis. And the hypothesis was that one hydrogen atom is created in every cubic meter of space once a century. In other words, steady state, everything stays the same always. Yes, the universe is expanding. Does that mean that the universe is getting less dense because all these galaxies are going away and there are no longer as many here as there used to be, so less dense? But no, the steady state theorist said, one hypothesis. Every century, one hydrogen atom is created in every cubic meter of space. And with that hypothesis, they could keep the universe going. It was a very attractive hypothesis. But the cosmic microwave background radiation knocked steady state theory out of the saddle. Fred Hoyle, you probably know the name Fred Hoyle. Fred Hoyle had to give it up, and he was the champion of steady state, one of the champions. Had to give it up. And now there's only one, and it's called the standard model of cosmology, and it's a Big Bang model. Okay? Yes?
Now my question can't be answered with certainty, that's like that gentleman's question, but if you could speculate, what do you and other scientists think was the state of affairs immediately before the Big Bang?
Well, you see, that's also an intriguing question. But in fact, it's a question I would ask. But in fact, it makes no sense. You see, time did not exist before the Big Bang. I know that's a hard thing to accept. But the Big Bang started the universe. It started time. It started space. As things started moving away and moving out, space was defined. By the way, try to define space or think of space with no objects in it. Empty space. You see, it's space and it's objects in a sense that tell you that you're in space of some kind. You get that information from the objects around you. Before Big Bang, there was nothing, I guess. And if there was nothing, if there was no objects, how do you know about time? You know about time because you see objects moving and you say, oh, he was there, but now he's here. And oh, that's time. It took a little second to move from there to there. But if with no objects, zero objects, before the Big Bang, there wasn't even any space. As far as we know, there was no space. So the question, I have no idea how to answer before the Big Bang. Yes. Okay, and then you. Just a minute. You? Yes.
Dr. Rigden?
Yeah.
I've heard it hypothesized that the expansion of the universe that we're experiencing right now is but one cycle of an oscillatory system. Bang, expansion, reaches a maximum, collapse into a dense whatever, explodes into another bang. Does this hypothesis still hold water?
Look, heavy water, yes. I'm not sure I understand what you were saying, but let me just comment. There's some mysterious things that we don't know how to answer. One is that the fundamental constants of nature, and there's only a few of them, are tuned in just a way that makes me possible and you possible. If some of those fundamental constants were changed by a whisker, I don't mean double, no. If they were changed by a fraction of a percent, we wouldn't be here. The conditions on this earth and the conditions in the would be such that we would not have, it would not be conducive to life. So the question is, what's the probability of a universe being created or coming into existence that has just the right value for the fundamental constants that I can stand here, I'm conscious, I'm aware of myself, I can think of things. I can think of what does this world mean? Why is that possible? Now there are people who feel we have to explain that. One of the ways of explaining it is that we're just one universe. There's a lot of universes out there. Statistically, they vary. A lot of them are not at all conducive to any kind of life at all. You wouldn't be able to exist there. And we happen to live, it's like a throw of the dice. Here's 1 million universes. And we are in the one that is conducive to life. Now, I'm not comfortable with that. But the point is, it's up to physics to try to answer why it is this universe is so finely tuned, just right, that life can exist. Now, if you're religious, you can do something with that. Okay? All right. Now, something else, and I don't know if anybody near your question, but something that's happened in the last 20 years, 25 years. How many have you've all heard of dark matter? Huh? You know what's interesting? In 1900, there were still many people who did not believe in atoms. I mean Nobel laureates who did not believe in atoms. And they thought, by the way, that we were at the end of science. They thought in 1895, people thought we were at the end, that we knew everything. And yet, they had no idea what this was. They had no idea about the nature of the material world. As I said, many didn't even believe in atoms. So what was this? They didn't know. So the whole world, in a sense, was still open for investigation and new discoveries. Well, we started learning about atoms, and hydrogen led the way. Now, we stand in 2009 at a very similar place. This, I understand. This, everybody understands in detail. But this constitutes about 4.5% to 5% of the entire universe. About 20%, 25% consists of dark matter. We don't have a clue what dark matter is. We don't have even a clue. About 75% consists of something even newer called dark energy. That is breaking the minds of astronomers, physicists, cosmologists. We don't know what it is. That could bring about new revolutions in the way we think about the world when we begin to understand it. Dark energy is a big mystery. And I'll tell you the way it was discovered. It was discovered that we're not expanding at a regular rate. We are expanding at an accelerating rate. So the expansion is speeding up. That goes back to a question one of you I think, asked. As this expansion speeds up, there's going to come a time, 150 billion years from now, when there will be parts of the universe that are out of reach for us altogether. Anyways, any other? Yes. Speak loudly, okay? Can you say that again loudly?
Is the universe becoming less dense?
Oh, less dense?
Yeah.
Well, because it's expanding. Yeah. Well, I would suppose it is. I mean, you see, look, what you have to understand is this too. We have the Milky Way. We have Andromeda. And we have a local group of, 15, 18 galaxies that are in our local group. They're gravitationally bound together. This local group is not expanding. Now, this constitutes a big space. But they're gravitationally bound. Okay? So the density within our local group, which is a big area. Look, Andromeda's 2 million... What? 2 million light years away. Okay? That's a long trek. And Andromeda, in fact, Andromeda is coming towards us. We're going to collide with Andromeda. I saw Saturday, when I was with Michael Turner, I saw computer simulations of the collision of Andromeda and Milky Way. Now, the claim is nobody here on Earth, or nobody hardly will know it. I mean, you may see the aurora borealis or something, you know. But the point is, the stars are far apart. And these two things can come together and collide. And there'll probably be some, maybe, you know, like those two submarines that hit in the ocean the other day. That's not likely. Or those two satellites that hit each other. That's not likely. And these stars, Andromeda and Milky Way, can go through each other. They'll drag each other's atmospheres, and they'll, you know, there'll be physical effects. But it's not likely that our sun, which will not be here, it's not likely that our sun is going to be smashed when Andromeda comes into us, okay? So the density issue, for large areas like our local group, the density is probably about constant. It's not expanding. Why? Because it's gravitationally bound together. Our local group, 16, 18 galaxies, whatever it is. Yes?
Is there anything that we can glean, any information we can glean about the early universe based on the original deuterium-hydrogen ratio, 3.5 to 10,000?
Anything we can learn?
Yeah, in other words, any properties that we can learn, any significance to that ratio?
Well, the only way, no, not beyond what I said. The only way we know, the only way that deuterium can exist is in those conditions, temperature, density, that existed from about 1 second to 1,000 seconds. And now remember, the Big Bang occurred. Immediately, the density of the universe, which was almost infinite right at the beginning, right at zero time, infinite, the density starts slowly decreasing. And the temperature starts slowly decreasing. And so we know what the temperature was about at 1 second and at 1,000 seconds. We know the temperature was about 3,000 degrees when the universe was 300,000 years old and atoms started forming. So we know the conditions. And that's, by the way, that's not a big deal. You start with something like, you know, a point, infinite density, infinite temperature, and then let it sort of explode of sorts. And their physical, general theory of relativity allows you to follow this. And so it's an amazing thing. It's an amazing thing that people, ordinary humans, have been able to gain such insights and knowledge about the universe we live in and have it come together in a way that you can say the evidence is really strong. I mean, it's analogous to, but very different, from Vollmer's formula. Vollmer's formula, calculated and measured, boy, they were almost exact. We have theories, but we have quantum electrodynamics, can calculate the magnetic moment of the electron to something like 18 decimal places. 0.12, about 18 decimal places. And it can be measured to about 18, 19 decimal places. Think of that. Think of that. By the way, you know all the name Richard Feynman? Think of something that you can express with a 0, a decimal, and then 18 numbers. And the error is only in the last number. The uncertainty is only in the last number. And the calculated and the measured value of those 18 numbers are the same until you get to about the last one, maybe the last two. So all of these are the same. Richard Feynman said, we know the magnetic moment of the electron to an accuracy which is equivalent to measuring the distance from New York to Los Angeles to an accuracy less than the dimensions of the human hair. Think of measuring the top of your table. You're lucky if you get it within an inch, or. But measuring 3,000 miles from New York to Los Angeles to an accuracy less than the dimensions of the human hair. That's the magnetic moment of the electron. We know it to that accuracy. It's incredible.
Measuring those properties, that hasn't changed in the last 100 years?
What?
Well, what I'm wondering is I trust the math, and I'm wondering if the calculated values are more accurate than the quote measured values.
Well,
I actually wonder if the measuring equipment hasn't progressed to the point to, or has measurement ability validated Angstron's original measurement?
The measuring equipment has gotten more sophisticated and more reliable. But there is this question. Are the fundamental constants changing? Fundamentally changing with time. Dirac, how many know the name Dirac? Paul Dirac. Paul Dirac wrote an important paper in which he proposed that the fundamental constants were actually changing. Now, they don't change week by week. They don't change century by century, or even millennia by millennia. You know, they change over periods of 1 billion, 5 billion, 20 billion years. But the implications to physics, if we could show that those fundamental constants are actually changing over long extended periods of time, the implications are profound. Let me just tell you one other little thing. Hydrogen. Hydrogen is simple. We know hydrogen. Now, you all know that there are antiparticles. There are anti-electrons, and there's an antiproton. What is a hydrogen atom? It's a proton and an electron. An antihydrogen would be an antiproton and an anti-electron. Jerry Gabriels at Harvard has made antihydrogen. He has slowed down in a particle accelerator. He has slowed down antiprotons and got them going, slowed them down enough where he could bring together antiprotons and anti-electrons, and they form antihydrogen. Now, what is he trying to do? He is desperately trying to organize his experiments so that he can get a big enough group of antihydrogens that he can shine a light through it, like that quasar through the light hydrogen cloud, and he can measure those same Vollmer lines of antihydrogen rather than hydrogen. Now, everything in physics, fundamental down to the sub-basement, predicts that they'll be exactly the same. That the antihydrogen energy states and the spectral lines will be exactly the same as hydrogen. But we don't know. And we're desperately trying to get enough antihydrogen accumulated. Gabriel's is probably working right now. Get enough antihydrogen accumulated so that he can do some spectroscopy with it. And let me tell you, if they're different, and when I say they're different, I mean if they're different in the 19th, 20th, or 24th place, and if it can be shown that that's real, not an experimental error, but if they're different even just, you know what I mean by the 24th place? You know? Think of a length of two things that are supposed to be identical. 12 inches, point, and then 18 numbers. That's the length. Now we have an anti-length, and we measure it, 12 inches and 18 numbers. But if the 17th and 18th are a little different, we got a big problem. And physics will have a major problem because that'll have implications at the foundational level. And by the way, this story, most of you, I don't see any 112-year-old people here. Most of you will be alive if you watch the papers, listen to the news. Gabrielle's is close. And Ted Hench won the Nobel Prize in what, 2003, I was up there on the board, up on the whatever. Ted Hench is working with Gabrielle. Ted Hench now owns the most accurate measurement in physics. I forget how many places, but he's a master at precision measurement. And he's working with Gabrielle's at Harvard, and they're going to get this hydrogen, anti-hydrogen, and they're going to do the spectroscopy, and we're going to see if physics holds together or whether it has to start again.
Let's just have one last question after 9 o'clock.
Okay. Maybe there's no last question. Oh, yeah.
Is entropy the statistical randomness of the system? And was the Big Bang, did the Big Bang statistically force you to be here today?
Force what?
Force you into existence?
Well, did you hear what he said? He started out with entropy. I don't know quite what you did with that.
I said that can be looked at as statistical randomness.
Oh yes, it can be identified absolutely with the disorder, the randomness of the system. So you're saying, is my presence here just a random thing?
Predestined from the Big Bang on down, trickling down to.
Well, you see, maybe so. I mean, maybe you can make that argument. This is related to the thing we just talked about a few minutes ago, namely that here we live in this very particular universe, which statistically, all odds are against these fundamental constants having just the right values, that life is possible, that self-consciousness is possible. Change one of them, and the average temperature would be such that we would not be able to be here. Change one of them, and other things would change, and we wouldn't be here. So the question is, was this range of values just a statistical thing? And if it was just a statistical thing, then this sort of suggests, well, there are other examples where the constants are different. We got the ace of spades, they got the ace of hearts, the king of hearts or something. Okay? So you certainly could look at our being here as a statistical consequence of things coming out of the Big Bang. We'd have to think about that and discuss it, though. I mean, okay? Okay. Well, you've been good.